of the room is videotaped. So if you don't want to be videotaped, then don't sit over on the side, which is why I'm going to sit over. So today, Costa will be presenting playing Atari with deep reinforcement learning. Actually, could you say a little bit about like your background too?
Yeah, of course.
You're working with.
Yeah.
All right, thanks.
Hello, everyone. My name is Costa Huang, and I'm a PhD student working with Dr. Santiago Antania in reinforcement learning with real-time strategy games. So this is kind of my specialty. So the paper today that I'm presenting is playing Atari with deep reinforcement learning. It's one of the more canonical or seminal papers that sparked the whole deep reinforcement learning with games trend. So today we'll be taking a look at that. And this URL, tiny.cc, blah, 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 that's the tiny URL for this presentation in case you want to look it up. Okay, so let's get started. So here we also have the address to the paper's PDF. So for those of you who have read the paper or only had a glimpse at it, the paper basically used EKey learning algorithm, also shortened as EQN, to train AIs to play Atari 2600 games. So for example, like Breakout, which would be this game right here, where you're trying to bounce this ball to destroy as many blocks up here as possible, and Pawn, which is you're trying to put this ball into the other side of the screen to win points. There are also Space Invader, etc. So by the way, there's always this terminology, deep XXX. My take is that deep XXX simply means the authors incorporated deep neural networks in the technique of XXX. So for example, deep Q learning, they just means they come up with an approach with Q learning that uses deep neural network. Okay. And now here's a short video. I managed to open it up, which doesn't seem to be the case. That's not why. Let's see if we can open it. Okay. EQN breakout. So this is the video that DeepMind released on the EQN paper that they trained the agents to play Atari, to play the breakout games. It just kind of stopped. Oh, right. Wait, what? For whatever reason, it's not shown up there, but if you have a chance to look it up yourself. Oh, never mind, it's playing now. Anyway, it just kind of stops and keep playing, but eventually as time progresses, the agent learns the optimal policy and learns to exploit the game and gain more rewards. I think there might be a delay to this somehow. Okay, so to understand this paper, let's delve into the details of it. The first thing that we have to understand is what is reinforcement learning. That's the basic underlying structure that they use to train the agent. The whole reinforcement learning operates under the structure of agent and environment interface. So that's basically you have an agent, which is this brain right here, and at each time step, the agent is going to fire out some action to the environment, and then the environment will give some observation back to the agent, along with some scalar rewards. And the idea is that hopefully the agent will take a look at this reward and think about what he has done to introspect and eventually learns, oh, this is maybe what I should have done to get a better reward. So that's the whole idea of reinforcement learning. I'll also give it an example. So consider a maze, and the agent initially was probably placed in the beginning of the maze, and then it's trying to go to the goal. and you get a reward of -1 per time step. And the actions available is north, east, south, and west. And the states are the agent's location in the maze. And now we can introduce some terminology that are very common in reinforcement learning. The first is policy. What is a policy? Imagine in this maze, if I give you the agent's position in the maze, you can tell me whether to go north or south or east or west. That's a policy, which is the actions that you want to take given the state that you're in. So for example, the policy of the agent in this particular state is to go up, and the policy of the agent in this particular state is to go right. So that's policy. And there's also this idea of value function following a particular policy, which is this little pi. Pi is usually used to denote policy, and v pi is just saying the value function following a particular policy. So for example, remember the reward is -1 per time step. So if you're here, it takes you exactly 16 time steps under the optimal policy to go to the goal. So here you get a reward of -16 because it takes 16 time steps. But as you get closer and closer to the goal, the value function of the state improves. And a related concept is what's called the Q value function or state action value function. Some people call it action value function, just a bunch of names. But what the idea is really is the given a current state and I execute a particular action, what's the value of the state that I'm gonna arrive? So for example, if I'm here, and then this is the S that goes into here, and then if I take the action of east, then we're going here, right? So the Q of SA is -11. So that's simply saying what's the value of the state that I'm going to arrive if I execute a particular action. So a very simple strategy to play this game, given a perfect value function, is to say, I want to look at all the available actions and simply take the actions that's going to lead to the better value function, a better value. So for example, I look at QA here, it's -10. QA here is -12. So I'm going to choose -10 as my action. The actions that's going to result in the -10. So that's why there's the connection between Q value and the value function, and why, and there's a reason why Q values is usually more commonly used because it's more general. It also covers actions as well. So remember, Q function takes into two values, S and A. So in the game where you have limited number of states and limited number of actions, it's actually possible to permutate what's called a QTable. And that's what this would look like. So imagine you have 500 states from 0 to 499. It's not 1 to 500, as you can see. But and then you have, let's say you have 6 actions. Initially, you might just populate your QTable with 0, but as time goes on, after some training, which I'll get into, you get certain values that specifies if you're at state 328, if I execute a particular action, I'm going to arrive at some sort of value. So in this case, if you look at here, the best action to take is north because you get a Q value of -1.970 or blah, 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 which means if you choose a specific action, you're going to result in a better state. Well, than the other state, at least. Okay. And Q-learning is a very greedy algorithm that always, well, almost always selects the actions associated with the biggest Q value. So it's going to look something like this, where if I run this game for an episode, it actually has some sort of exploration strategy as well, because you don't imagine if you just have the QTable and then you don't do any sort of exploration. You're always taking the actions associated with the largest Q value. You might you may not ever explore some other possible actions. So there's this idea of epsilon greedy exploration, where you choose, you set an epsilon to some number, let's say 0.2, and then you randomly generate a number from 0 to 1. And then if that number is less than epsilon, then you do some exploration. Otherwise, you exploit the QTable. So this is what this does. But anyway, so if you're doing epsilon greedy exploration, then you do random actions. Otherwise, you always select the action that associates with the biggest Q values. So in this case, it'll select 1.97, negative 1.97. But if you have a case of a draw, then you randomly select one of them. So that's the Q learning. And there's going to be an update here that's sort of hidden, which I'll get into in the next slide. So this is the core of the algorithm, the update rule of the Q learning. Remember, initially the QTable starts with just 0, 0, 0, one of the ways you can initialize it. You can also just initialize it randomly, but 0, 0 is easier for theoretical analysis, I guess. And this would be the update rule. This is actually taken from Wikipedia. They had an awful formula before, and I just realized I can modify Wikipedia without like approval from them in the mediator, so I just modify it to do something that I like. But this is what I like. Forget about what's on the left side for a moment and focus on the right side. So there are a couple things. The first is the Q value at a current state. Given a state and given an action, this is the old Q value. There's also an idea of a new value, which is the reward you get after executing this particular actions from this particular state. And then plus the discount factor, which is a number from 0 to 1. The discount factor is used to tell you that rewards that are immediate are in some way more important than rewards in the future. So it gives you a way to tune how short-sighted or far-sighted you want the agent to be. So reward plus the discount factor times the Q values given the next state. The Q values with the actions that resulted in the largest Q value. If that makes any sense. But it's basically maximum over A given the next state. Following, again, you have to follow a particular policy. In this case, I guess the policy would simply be select the best Q value. Right, so this is an estimate of optimal future value. And then this value, in a sense, really should be the same as the old value. Because the old value really should capture everything that's going to happen in the future. And on the new value side, this is what's going to be happening in the future. And if you think about it, the Q values, if they're all initialized with 0, then this reward is going to dominate. So if this is 0, this is 0, this is going to be 0, you just have reward. And then they're going to have a difference between the new value and the old value. And that's what's called the temporal difference. Because this is what's happening in time step t, this is what's happening at time step t plus 1. So the temporal difference times the learning rate, which is, again, some parameters that you can use to tune how fast you want the QTable to be updated. And then you add that to the original Q value to update the Q value. So that's how the Q value is updated. So initially, you're kind of updating it based on a reward, but then the Q values gets updated, you get some sort of values over here. And the whole idea of Q learning, of DQN, is to say, okay, forget about what's on the left-hand side. I'm just gonna minimize the loss, which is the mean squared error between the new value and the old value. Because as we tried to say before, these values really should be the same. Because this is saying from ST and executing AT, this is what will happen after you execute the action AT. So that's the whole idea of DQN, but of course they have some tricks along the way. And this is the DQN full algorithm that is presented in the paper. So they initialize this thing called a replay memory, which records all of the transitions, which are from given the current state and the actions you executed, what's the reward you're going to get, what's the next state, and whether the episode has finished. So it's 5 values tuple that has been pushed into the replay memory. And then eventually they're going to sample from the replay memory to learn from it. Okay, but they initialize the replay memory, and then they initialize a Q function with a neural network. And then they, for each episode, they initialize a state with probability epsilon selected random action EKey. So that's the epsilon greedy exploration we're talking about. You want the agent to do some sort of exploration instead of just always exploiting the QTable. Or in this case, it's approximation of the QTable by using neural networks. Otherwise, you select the actions that will lead to the best Q values. Execute the actions in the emulator, observe the reward T and image XT plus 1, and then you pre-process them somehow, which I'll talk in later stages of this presentation, and then you store the transition, which are 5 values. They really have 4 values. Let's see what's missing. State, right? They don't have the terminal condition, but that's okay. That's just a minor implementation issue. And after that, they sample a mini batch, which in the paper is usually 32 transitions from the replay memory, and then they're going to learn it. And essentially, they're learning it based on the maximum. So this is the temporal difference that I was talking about. Minimize this minus that. So that's this part minus the original Q value. And this is the next state Q value. But they also have some issues with terminal conditions. Essentially, if you're at the terminal state, then you really should be reward because there's no future from the terminal state. But otherwise, you estimate the future by using this. Probably shouldn't. Let's just. Okay. By the way, this might not be a very long presentation, but I'll go into it. Open mic. Actually, before I sort of talk about the code, maybe it's more interesting to look at something more visualized, more interesting, in my opinion, kind of. But so I try to reproduce this paper by using the pond environment, which is you have 2 paddles, and then you're trying to put the pawns into other people. You'll see. But the reward doesn't mean anything. But the cool thing is, I can show you the agent performance at each time step. So at the episode 1, the agent is doing random things. So you see those numbers 3, 4, and 0. The rewards that are given is something like this. You receive a negative reward if you lose a game, and if you get a positive reward if you win a game. So initially, the agent is randomly initialized, so it's performing really, really badly. It loses all 20 games. But as time goes on, performs better. But not here. There's actually a bug. This really should be the number of episodes. I'm going to pose an issue in the library that I use for this. This really should be episode 20 or something. But it's still performing really bad. it's winning. So that's good. So it's learned to somehow moving closer to the shop, right? Let's keep going. So it would appear that our agent has found something to abuse, right? So that would be wait for it to drop here and always hit through this trajectory. And then somehow the built-in agent is able to handle that, and it just keeps exploiting. And that's part of the characteristics of Q learning algorithms is that it's always exploiting the same. It's always exploiting things, and sometimes in a very deterministic manner. So now our agent wins 20 games. So that's why in the reward graph, you see that the agent is close to 20. But yeah, everything sort of after that is kind of similar, where the agent will try to abuse the, this trajectory. But anyway, it kind of solves the game. Okay, now we get into the sort of details of the algorithm, and which is also where the preprocessing comes in. So usually for reinforcement learning algorithms, we just have this part. That's it. But in this case, the DeepMind guess has a lot of wrappers. So for example, they have, so the wrappers are the wrappers you put upon the environment to either help it or something. So for example, the first wrapper is to say, if the pawn has the ball in it, just fire it without learning to fire it in the first place, because that's kind of a waste of time. So that's sort of the fire reset environment. And then they also have this max and skip env, which does some sort of pre-processing, where they say, I'm going to skip the number of frames, and for each of the frames that I skipped, I'm going to take the maximum value out of those each individual frames across, let's say, 4 time steps. And they also have preprocessed frame 84, which is to resize the frame from 210 by 116 by 3, which is the original resolution by the image, and reshape it to 84 by 84. There's some issues with PyTorch where you need to, usually you have image height, image weight, and channels. In PyTorch, it's opposite. It's something like the channels, image width, and image height, or something like that. So you need to move the axis a little bit. And then there's also a scale float frame where they essentially divide everything by 25. So they normalize everything in a range from 0 to 1, because each cell in the observation is a pixel of 0 to 255. They also have a buffer wrapper, which honestly I don't know what it does, but it doesn't look like it's doing a lot, does it? Because when you reset it, it has a buffer that literally doesn't seem to be doing anything. It just says I'm initializing an array, and then I'm doing some sort of observation, some sort of things to record the observation. Oh, it is, I guess. It's recording the observation, and then it's returning the buffer stat. So it's doing something, but I don't think it's that important, at least for that. Other things might be very important, like the fire reset or max skip, but maybe the buffer wrapper isn't that important. But then we get to the implementation. So I like using parser, the command line arguments to tune the hyperparameters. From my perspective, it's better than a lot of the reinforcement learning frameworks, which use like a very specialized configuration files that are impossible to read. But I have a lot of arguments, and reproducibility is very important. So I depend lines to seed it, because each Python library have their own kind of seed or things like that. But even that, it doesn't exactly work with this case because of all the wrappers. Somehow the reproducibility is not guaranteed. I'm not very happy about it, but I'm also not in a big interest to fix it because but playing Atari is more computationally expensive, so that's something that I hope not to do for research and compete with the big guys like Google or DeepMind. But then you have this replay buffer, which you append the transition into the buffer, and then when you sample it, you sample a certain number, in this case usually n equal to 32, and then you sample some states, some actions, some rewards, well, of course, corresponding ones, and whether the episode is finished. And then initialize the key network, which is you have a convolutional network, ReLU, Com2D, ReLU, Com2D, ReLU, and then after processing the images, what you want to do is to flatten it and then pass it into a simple linear neural network. Also a linear layer, a ReLU layer, a linear layer. This is the tuning of this is more of an art than science, unfortunately, at this moment, but this is kind of a little bit science. And then you define how to forward it, which, as I said, is to use the convolutional layer to process the images, and then you flatten it, which is this -1 part, and then you use the fully connected layer, which are the linear layers, to output the final probability distribution for reactions. You initialize everything, and you start running things for steps in each episode. If the random number generated is less than epsilon, you do some exploration by sampling from the action space. Otherwise, you take a look at the thing. You take a look at the values that's generated by the Q network, and then you find the actions that are associated with the best Q value. And then you train, where you're basically trying to calculate the target, which is given the next state, what is the best Q values for the next state. And then, you calculate the things that are covered in the update rule of our slides. And then you run the script, and then you generate things like this, which also tells you quite a lot. Like a bunch of things. Like, for example, so look at here, right? The system memory utilization looks perfectly fine, right? I had a previous run that blows it up. So that's pretty funny. So you see the memory usage go from about 50% to 100%. My computer was very slow for 2 days, and I couldn't figure out what the bug was. And then I realized I set the replay buffer to be too large, and then I tweaked it and solved it. But yeah, it's overall very a good tool for me to record all of the experiments, and also the files that are associated with is also recorded in the cloud as well. Any questions? Go ahead.
So I was wondering, how does the built-in agent work there? Like the built-in agent?
Oh, the built-in agent? I have no idea, but I would assume it's some idea, I can guess. It's probably something like, if I look at the ball, calculate the position, how far is the ball from the racket, I guess, and then adjust its position accordingly. Like, make some predictions about the velocity, angle, and then move its position accordingly.
Was there a way that they could play this with real users?
You can make it so, yeah. Go ahead.
So the only argument to the Q function is the state. Oh, okay. So it's like Q.
I see. Yeah, there's actually a minor thing with the implementation. Good question. So When we were showing the slides previously, the key value is taking the states and the actions, right? Here, when you see the key values are being asked, it's just the Q network, or in this case, target network, forward just the states instead of the actions. So what it does is that the Q network generates 6 values. So there are 6 actions, and then it generates 6 Q values, and then you select the largest of them. And you find out the index, which is what the artifact is. So you always select the actions that are associated with the largest Q values.
Got it. Thank you.
No problem. Good question.
So what are the? You said there's 6 actions.
Yes.
But isn't it just up and down?
That seems to be the case, but I don't know what the other action does, which I should know. But I would imagine one of them is fire, which is why they have like a fire reset environment, which for an environment where the user need to press fire for the game to start, you need to press it. But yeah, it really should be just up and down.
Okay. And then the last linear layer had 512. Shouldn't that be 6?
The 512 here?
No, yeah, the bottom output linear.
Here?
Yeah. Oh.
So that's the action space on which is the number of actions. So it will be 6 in this case. Yeah, go ahead.
So my understanding is, like, in general, the Atari has 6 actions, and then like they disable some of them for certain games. So I think for Pong, you can only go up and down and do fire, but then they just, like, the network learns that it doesn't do anything if it uses any other action.
Right, so just kind of ignore the actions that doesn't have any fun.
Yeah.
I think that's the case. Like if you're doing in sort of a more advanced way, you can mask out actions. But that's not what's being implemented. Yes, sir.
Is epsilon greedy sort of the standard? If so, why not like UCB or some other standard algorithm?
Yes, epsilon greedy seems to be very common with the DQN. As far as UCB, think how that would work out.
They made this big deal in the paper about how the environment can be stochastic, and I was like, oh, well, that seems like a prime candidate for UCB.
Right. I just did a presentation on UCB to my advisor. Remember what it is about. I just remember it was you have a bunch of actions, and then you're trying out. Right, but UCB is for one states only, right? You can have a UCB instance for each different states. The problem with the UCB is that in this case, you have 500 states. With epsilon greedy, you can treat it sort of like a, not just a bandit problem, but rather it's more general because you have multiple different states. So you're almost running the same epsilon greedy with multiple different bandits, but you couldn't do that with UCB. Yes.
Sorry, I have a couple questions.
Yeah, go
So,
ahead.
when you get a reward, when you win the game, you get a reward, and that reward goes to all of the episodes, all of the states in that episode. Is that what the reward is?
So I think instead of only giving you a reward in the end,
Yeah.
I think what it does is actually, say you have 10 time steps. You win the game at first time step, it gives you a +1, and then the game doesn't finish, you get 0. The game doesn't finish, you get 0. You lose the game, you get -1. And then you win a game again, you get +1. Does that make sense?
But, so there's no incentive to win the game faster, right?
Actually, there is.
There is?
There is, because of the discount factor.
Okay.
The discount factor is saying rewards in the future are worth less than immediate rewards. So you always want to finish the game as fast as you could.
And then, so it always, I've always been confused about games where the space of actions is essentially like infinite, right? So
Right. So
how do you? Yeah, sorry.
go ahead.
No, how do you do that?
Right. So that the case you were mentioning, that's more of a continuous case situation, which I also have examples for. but it's okay. Come on. Oh. Okay. So for continued case, totally different things, but unrelated to this paper, but also very interesting. Incredibly difficult to debug. But I also have some interesting things to show. The view reports. This is sort of a more comprehensive benchmark that I'm doing for all kinds of reinforcement learning environments, because I think it's important when you have interactivity and you can click on any of those runs to see the hyperparameters and reproduce it yourself, instead of watching a paper that just have like a gazillion pictures and you don't know which code that generates those. So, but anyway, so over here you can see, like again, little animations there here, comparing different runs. But the ones you were mentioning about is more continuous case. So the example would be Walker 2D. So like learning how to walk, which the computer is regrettably kind of slow. And okay, I'll just click on one of those. It's lagging really hard because there are hundreds of videos being loaded. I'll show the demo first, and then I'll talk about the details of how you deal with a continuous action space. It's also very interesting how you deal with that. What I'm gonna do is just smooth it, because this is not really that readable. Did I just delete all of my videos? Okay, well, there's no videos, no more fun for that. But the idea is for, let's say you have an uninnumerable number of actions, let's say continuous action spaces. You want to know the, let's say the speed or acceleration at which you want to accelerate the car. What they do is, so pen. So what they do is, so imagine you have 3 continuous values you want to generate. The speed. Okay, I'll just stop. Okay. If this doesn't work. Got it. Let's say you want to generate acceleration, speed. What they do is they generate a mean and their standard deviation, which is this, right?
Sigma.
How do you write sigma?
The line goes, dash goes the other way.
Yeah, close enough. But yeah, you generate this. And this. So what you do is you use a neural network to generate the mean and the standard deviation, and then you create a normal distribution, and then you sample the actions from that normal distribution to generate the actions. With the DQN, how to optimize it is not obvious, because you couldn't, so in the Q value, like if you have a continuous action space, and then even if you have a normal distribution, it's not exactly defined the values that maximizes the value of the most distribution, I guess. It's not obvious. There are ways you can do it. For example, one thing you can do is you fix the neural network, and then you input the state. You want to find the state that stated action that maximizes everything, right? what you can do is you fix the neural network and you use the action as parameter, and then you pass it through the neural network. Instead of optimizing the neural network, you optimize over the actions, so that you find the actions that maximizes the whole thing. But that's something that's done for the EKey one. For other things like actor critic, which there's no context for this paper, but for actor critic, you can use, if you have a normal distribution, it's much straightforward to calculate the update rule. So yeah, there are ways to handle it.
Have you tried making two DQN agents compete against each other?
You can. It's not implemented in this case. I don't know whether you can do that with Atari, because they're written in C++. I know nothing about C++. Actually, they implemented. I think they implement the emulator, so they're using like code, like I don't know, assembly under the hood to execute all of the games. But, if you want to have Atari play against each other, you're probably better off to start from scratch, write it yourself. But if you want to do that, might as well just try something else, like my research project, which again, the video is not showing for some reason, but it's RTS games. You can program it in a way that you have agents competing against each other.
So, I guess a general criticism I hear about reinforcement learning, and I wonder if you could give your take on this, is that it's not going to lead to like, I guess you need lots of trials.
Yes.
So like, for example, we don't learn by driving off a cliff 1,000 times
Right.
and then getting a negative reward, right? So how do you see reinforcement learning playing in sort of the bigger picture of general intelligence?
Yeah, there's something interesting to show. Estimating human prior. So I think the answer to that question is that human has a lot of prior knowledge, but we're not really sort of noticing it that much. So for example, this research group, they did an experiment where this is just a normal case, right? In a way, the neural network really sees this. Imagine you're driving a car in this sort of situation, with everything that's not in your prior knowledge. You'd probably drive off a cliff as many as the neural network agents would. So from my perspective, I think future directions would be either hierarchical reinforcement learning or somehow transfer existing knowledge, or transfer reinforcement learning, because we really shouldn't have the agents to look at this every time. Yes, go ahead.
Do you think there's a connection, just kind of going on the professor's question, between evolutionary learning and reinforcement learning, that you're sort of, it's almost kind of evolutionary learning boots up for the human a certain amount of prior knowledge, and then you kind of on top of that, you reinforce more?
As far as I understand, neuroevolution uses like mutations or crossovers, right? But the problem is with that is, like, there's, as far as I know, there's some works that gained interesting performance with games, but in general, it doesn't seem to have a very good theory to optimize this over. It's mostly trial and error. Like even in reinforcement learning, the standard approaches are trial and errors, but they have this thing like a policy gradient. You know, sort of the direction. They have like a convergence guarantee in a lot of situations. Well, theoretical convergence guarantee in a lot of situations. But I don't think that would be the case for neuroevolution, because the optimization is too primal, because you're doing crossovers and mutation. I don't think it's very clear as to how you optimize this over very complex games. I think neural evolution is more used for like hyperparameters tuning because those things are more random than actually have a gradient to optimize the silver. I see that in your eyes. Then.
No, I don't know.
Oh, okay. You had a question.
All right. Let's think.